Hello everyone, this is Fiza from group 316. Today's our topic is cutaneous sensation, mechanoreceptors, receptor classification. Receptors for touch, pain, and temperature are structurally simple. Nociceptors and thermoceptors are grouped with mechanoreceptors due to structural similarities. Nerve cell structure. Simple receptors are categorized based on the geometry of their dendrites endings. Free dendritic endings. The endings are small nerve fibers that permeates body tissue similar to the plant root is in soil. They are distributed widely throughout the body and includes nociceptors, thermoceptors, and some mechanoreceptors. Some free ending wraps around the hair root responding to hair movement, while other endings in flat disc at the epidermis. Encapsulated dendritic endings. These endings are enclosed in connective tissue capsule resembling plant bulbs and are primarily mechanoreceptors. Variations in structure corresponded to the specific mechanical stimuli, light, pressure, high pressure, and strain or vibration. Response to mechanical load. The mechanoreceptors response to the mechanical load, which can be described as a pressure or stress. The load is typically time dependent and the design of mechanoreceptors allow for efficient responses to the specific loading and characteristics. Adaptation types. Mechanoreceptors can be classified based on the adaptation to the load changes. Slowly adapting response to the intensity of the load. Other types may respond to the rate of the change of the load. Mechanoreceptors. Mechanoreceptors are sensory receptors that respond to the mechanical stimuli. They can be classified into two types: slowly adapting and rapidly adapting receptors. Panicans corpuscle. The panicant corpuscle is a type of mechanoreceptors found in the skin. This is shaped like a rough ball and is approximately 1 to 2 mm long. It has a layered structure with up to 6 layers of flattened cells surrounding a central core. The panicant corpuscle is sensitive to vibrations and serves as a monitor of the rate of the change of the load. Structure and functions. The panicant corpuscle has a central core surrounded by a layer of elastic membranes. The membranes are filled with a viscous fluid that flows slowly in response to change in pressure. When a load is applied slowly, the fluid flow and the pressure remains hydrostatic. When a load is applied rapidly, the fluid cannot flow quickly enough and the pressure becomes non-hydrostatic. These cause the elastic membrane to stretch and the central core to be stimulated. Model of panicant corpuscle. A simple analytical model of a panicant corpuscle has been developed. The model consists of a series of elastic membranes connected at one end and filled with a viscous fluid. The model can be expressed in terms of a combination of spring and damper elements. Particle discrimination and density of mechanoreceptors. Spartical discrimination is the ability to distinguish between two nearby stimuli. The density of mechanoreceptors can be estimated by stimulating adjacent site and adjacent sites and measuring the minimum distance required to distinguish between the stimuli. The result of the experiment shows the density mechanoreceptor is lower than the expected. Density of mechanoreceptor is different body in different body parts. The density of mechanoreceptors vary across different body parts. The highest density is found on the tip of the tongue. The lowest density is found in the back, on the back. Thermoreceptors. Thermoreceptors respond to heat energy stimuli. They are relatively few. Thermoreceptors in human skin with a typical density of 5 to 10. The thermoreceptors can be subdivided into steady state receptors and that monitors constant temperature. Dynamic receptors that responds the rapid change in the temperature. Hot detector that responds to high temperatures. Cold detectors that responds to the low temperatures. Density of cold detectors. The density of the cold detectors in the skin is generally an order of magnitude higher than that of the hot detectors. Steady state detectors. Steady state detectors are relatively inactive at normal skin temperature. Thank you. Hello everyone. This is Fiza from group 316. Today's our topic is influence of elastic walls. Elasticity of blood vessels. The analysis considers the elasticity of blood vessels, particularly large arteries, rather than assuming rigid walls. Windick-Kessel theory, developed by Frank in 1899, this theory modeled the aorta as an elastic reservoir containing instantaneous volume and pressure through a equilibrium equation. Outflow determination. The outflow rate from the aorta is influenced by peripheral resistance. Volume change calculation. The change in volume of an elastic walled vessel is related to internal pressure, radius, thickness, and Young's modulus. Proportional relationship. For small change in radius, the change in volume is approximately proportional to the applied pressure. Flow out of vessel. The outflow rate Q out is determined by the peripheral resistance R given by Q out is equals to P by R. Total flow into reservoir. The total flow Q is the reservoir account for both the change in volume and the outflow. Proportional propagation of pressure plus in elastic tubes and the Monks-Cortius equation. First order linear differential equation. The equation discussed is a first order linear differential equation similar to those solved in earlier chapters related to the viscoelasticity. Pressure time wavefront. Solutions for specific form of inlet flow based on the heart flow can be used to predict the pressure time wavefront in the aorta. Monks-Cortius equation. This equation models the flow of an inviscid fluid is an elastic tube using continuity and momentum equations. Assumptions for the model. The fluid is homogeneous and isotropic. The fluid is incompressible. The fluid is inviscid, non-viscous. Flow characteristics. The cross-sectional area of the tube varies with time. The velocity v minus z does not vary across an cross-sectional but varies along the axis and with time. Pressure is a function of both axial coordinates and time. Continuity equation. The continuity equation for the flow is given by. Here is the equation. Simplification assumption. The equation can be simplified under the assumption that the pressure plus move slowly relatively to the speed of sound in the fluid and has a long wavelength. Pressure area relationship. The pressure at any cross section is an function of cross sectional area A expressed as this formula P is equals to PA. Assumption regarding the distinction. The distinction at one cross section does not affect the distinction of adjacent cross sections. The viscoelastic behavior of tube walls is not considered. Differential relationship. The time differential of area can be expressed in terms of the pressure differential. Linearized momentum equation. The momentum equation simplifies by the neglecting convective acceleration. Mons-Cortic wave speed. The speed is known as the Mons-Cortic wave speed, named after the Dutch scientist who developed the linearized theory in 1878. Typically flow speed. The typically blood flow is the aorta. The speed of propagation of the pressure plus is approximately 4 meter per second, which is faster than the peak flow rate of above 1 meter per second. Speed in collapsible veins. In collapsible veins, the speed of propagation may be as low as 1 meter per second, which can lead to special phenomena similar to the sonic flow. This point summarized the key concept related to the propagation of the pressure plus in elastic tube and their implications in biological systems. Thank you.